are your inverse functions for exponential equations, right? So we had talked about how, what the logarithmic function will do, the exponential function will undo, and vice versa. And of course, remember that conversion between the logarithmic functions and the exponential functions. So you should be able to, convert them back and forth into the two formats. So make sure you're comfortable with that. And then we had also talked about common logarithms and natural logarithms. So remember, when we're talking about a common log, basically we are saying instead of writing it with a base 10 logarithm, we abbreviate it just as log of x. And with natural logs, which is a base e logarithm, we again abbreviate it only as ln, the natural log of x. And again, you will see those same conversions between the common log and its equivalent exponential notation, and same thing here with the natural log and its exponential notation. So what we actually want to start out with today is talking about the graphs of these logarithmic functions. So when we're talking about graphing these traditionally, and actually if you guys have seen the video lecture for this section, then you will know that, typically when we are graphing these functions by hand, we actually start out by graphing the exponential function. And then the idea would be, you would create that table, the x and y table, and then we would just reverse our ordered pairs for the x and y values, and then use that reverse table to create our logarithmic function. So traditionally, that's how you actually draw your log functions. You start out by drawing the equivalent, using that same base, draw your exponential function, and then you draw the logarithmic function based off of that. So let's take a look at, what the graph for a function like this would look like. So we've got f of x equals log of x with base 6. So again, we'll use our Desmos. So the equivalent function for that as the exponential function would actually be 6 to the power of x. And then if you remember from section 2.5, we use the line y equals x as our line of reflection. So I'm going to graph that also, and then we'll show you what the logarithmic function will look like. So this will be log of x with base 6. Okay, so here you can see our graph in the red is going to be the exponential function. So this guy here is the 6 to the x. The graph in green is our logarithmic function with base 6. And then, of course, the line y equals x, which is in blue, is acting as our line of reflection. So basically, the idea is you should see that the two graphs with respect to this blue line are going to be reflections of one another. So just to compare the properties between our logarithmic and exponential functions, let me actually zoom into this a little bit. Okay, there we go. So you should see that, in our exponential function, we have a y-intercept at the point 0, 1. So we know that point reverses, and it actually ends up becoming an x-intercept in your logarithmic function, and that's going to be the ordered pair 1, 0. If we talk about the domain and range, and I think I had mentioned that last time, the domain for our exponential function, of course, goes from -infinity to +infinity. The range, as we had talked about last time, goes from 0 to infinity, and we do not include 0, and that's because we have a horizontal asymptote here at the x-axis, which is our equation y equals 0. So, since the logarithmic function is the inverse of the exponential function, that actually means our domain and range are going to flip, right? They're going to change. So now the domain, and you can verify that by looking at the graph, ends up becoming 0 to infinity, not including 0. The range will end up becoming negative infinity to positive infinity. So just switching the order from our domain and range from the exponential function to the logarithmic function. Additionally, you will see how you have a horizontal asymptote for the exponential function. So you actually end up having a vertical asymptote right here, and you can see that this one right here, our graph will get closer and closer to the y-axis, but obviously it's not going to touch or cross the y-axis, so you end up getting your vertical asymptote at the y-axis, which again as an equation will be x equals 0. The other thing that will actually stand out in these functions is you will actually see how if we go from left to right, our exponential function goes up. Same thing is happening on your logarithmic function. As you go from left to right, your function is going up. So in both our exponential and logarithmic function, because the base of our function is a number greater than 1, so if your base is a number greater than 1, remember both of these are going to be increasing functions. So just a nice comparison between, what happens with your exponential function and its inverse, the logarithmic function. And, of course, this will be true for whichever base you are looking at. And, all of this is mentioned in your handout with your notes. So let me just point that out. So we are talking about using the line y equals x as the line of reflection. You should notice that when you have a horizontal asymptote at the x-axis for the exponential function, that of course ends up becoming a vertical asymptote at the y-axis for your logarithmic functions. Of course, we know our functions are going to be one-to-one because obviously we can find their inverses. We talked about how these functions are increasing functions. For that matter, look at the graphs for your common log and your natural log functions. They also look very similar to the graph we just talked about. So they are also going to be increasing functions. You can see our x-intercept is at 1, 0. You have your vertical asymptote at the y-axis. So a lot of those properties will definitely stay similar. So just keep in mind when your base is greater than 1, your function will be increasing. If your base is going to be between 0 and 1, your function will be decreasing. So again, just to show you the graph, is log of x with a base of 1. Okay. So let's change our exponential function also with a base of 1/6. And you will notice how the direction of our red graph changes. And then to do the base of 1/6 with the logarithmic function, I was working on this yesterday and it didn't seem to let me type in a fraction. Possibly I'm doing something wrong, but just to save time, I'm actually going to go ahead and put my decimal equivalent for 1/6. So you at least kind of get to see what the graph will look like. So, obviously a lot of those properties are still staying the same. You can see our x and y intercepts for the both of our exponential and logarithmic functions are in the same location. Of course, the graph in the red is your exponential function and the graph in the green is our logarithmic function. Our vertical and horizontal asymptotes are also in the same location. We still have a horizontal asymptote here at the x-axis and a vertical asymptote here at the y-axis. The only difference that you are seeing between the graphs we saw before and these ones is, of course, both of these functions are decreasing. As you can see, when we go from left to right, our function values are decreasing. Same thing on the logarithmic function. As we go from left to right, our function values are decreasing. Domain, range, all of those properties are going to be the same. The only difference is these guys are now decreasing functions. Did anybody have questions on this part? Okay. And then, again, in this little box over here, we're listing all of these properties. So increasing functions when our base is greater than 1, decreasing when the base is between 0 and 1. We will have an x-intercept in these logarithmic functions at 1, 0. Y-axis is our vertical asymptote. So remember, as an equation, you write that as x equals 0. Domain for logarithmic function goes from 0 to infinity, not including 0. And range will, of course, go from negative to positive infinity. We know these functions are 1 to 1, and then, of course, they are inverses with the exponential functions. Now, with our transformation format for these logarithmic functions, you will see this is what the general form of our equation will end up looking like. So inside the parentheses, you have x minus h. So that, of course, is where the horizontal movement happens. So if it's x minus h, remember that means that h itself is a positive number. And of course, if it's positive, that makes our graph move to the right. If you see x plus h, then remember that means h itself is a negative number. And then, of course, that means your graph is moving to the left. By adding this k value at the end, and again, you can add or subtract that. But if k is a positive number, that makes our graph move up. If k is a negative number, that makes our graph move down. By multiplying that b in front of the logarithm, that will give us our stretching or shrinking. So again, if b is greater than 1, the graph stretches. And of course, if b is between 0 and 1, the graph will shrink. And then if you have a negative sign on the b, then remember that's when it creates that reflection in the x-axis. So you've got this example over here in your handout that you can look through. But basically, remember those properties for transformation stay the same. Obviously they just look a little bit different with the logarithmic function. So let me actually show you a couple examples over here before we talk about the next set here. So we have looked at examples similar to this last time. So you've got a couple examples on that, but let's talk about how you will graph your functions here in MyMathLab. So as you can see, this one is about log of x with base 5. And the first thing they want us to do is complete this table over here. So you can basically rewrite this function as y equals log of x with base 5. And when they're asking us to do these ordered pairs, basically what you are doing is replacing that x value with the values given to us over here. So for the first one, you will have x equals 1/5, and you're basically trying to find the y value. Of course, we'll come back and repeat that process with log of 1 with base 5. And then the last one would be log of 5 with base 5. And you're trying to find those corresponding y values for each one of these equations over here. So let's start with this first ordered pair here. So we are given y equals log of 1/5 with base 5. So this is where, you need to remember to convert these into the exponential notation. So that is, if you are given log of x with base a equals y, then remember converting this to the exponential format, you take base a raised to the power of y equals x. So when we do that here with our first ordered pair, our base is 5, we raise it to the power of y, and that equals 1/5. Now, it's when you have that 5 in the denominator, it's understood that it has an exponent of 1. So when we move that 5 from the denominator to the numerator, it would, of course, end up becoming 5 to the power of -1. And remember, this is where we use that one-to-one property for our exponential functions. So once we can get both of these bases to be equal to each other, we can basically end up saying y equals -1. And so that's how you actually come up with this ordered pair of, 1/5 for the x value, and then your y value would be -1. And that's obviously the same process we would use for the second and our third order pair over here. So if we did the second one, we are given y equals log of 1 with base 5. So again, converting this into exponential notation, you will have 5 to the exponent of y equals 1. Now think about this. When do you get the answer of 1? What does the exponent have to be for our answer to equal 1?
Zero.
Yeah, very good. It's the zero exponent rule. So when you have a zero exponent, that's the only time you get 1 as your answer. So that, of course, tells us that our exponent over here is going to be 0. So this will be ordered pair 1, 0. Alrighty, very nice. So let me see what you guys can come up with for this last ordered pair where you have y equals log of 5 with base 5. What do you think the y value should be in this case?
Isn't it just 1?
Yeah, very nice. Because when we convert this into our exponential notation, you're taking this base 5. So it will be 5 to the power of y equals this 5 here from the parentheses. And of course, you can see no exponent means you have an exponent of 1. So since our bases are the same, we can go ahead and say y equals 1. So then, yeah, this y value will just end up becoming 1, and we have the ordered pair 5, 1. Alrighty, very nice. So let's plug these values in. And if you actually remember, I had kind of mentioned this last time with that first ordered pair. You can actually see, whenever you have a base which is a whole number like this, a 5, but then your x value is 1/5. So you have a whole number and a fraction. So whenever you end up with a combination like this, you do actually end up getting a negative y value. So it's kind of a nice thing to remember, when you're working through these kind of examples here. Alrighty, let's go ahead and check our answer over here. And then the graphing for this is actually going to be very similar in process as you had done for the exponential functions. So obviously remember to select your logarithmic tool. Just click anywhere on the graph and this little window will pop up. So remember, you only have log of x with base 5. So there's no stretching, shrinking, shifting, any of that happening. All you do is take that base e and change it from e to your base 5 for this function. And then, of course, that will change your graph accordingly. And that's all you have to do. Just save your graph after that. And you can see, this graph looks very similar to what we were talking about before. You've got your x-intercept at 1, 0. You can see there's a vertical asymptote again at the y-axis. For that matter, you should be able to verify the domain and range as what I had shown you with those other graphs in there. And again, since our base is 5, which is a number greater than 1, of course, you can see this is an increasing function also. So all of those properties you should be able to verify by looking at the graph. So the last part here, they're just asking you to type in your domain and range. So remember, the domain goes from 0 to infinity, not including 0, because obviously we have that vertical asymptote. And then range goes from negative to positive infinity. Any questions on this one, guys? So again, remember your graphing is just changing those values in the little box that pops up. This will be very similar to that. So, you know, work on this when you do your homework. And of course, if you have any questions, you know, let me know. This example here is honestly just asking you to rewrite this in the exponential notation. So remember, you're using that conversion from the logarithmic equation to the exponential equation. So what do you think this guy will come out to be when you rewrite it in the exponential equation? And you know, give me the entire equation. For now, ignore the fact that they're giving you equal to 9, because you should be able to convert this from logarithm to the exponential notation, because in every example, you know, they're not going to give you part of the equation. So make sure you're able to do that without any help. So what do you think this will look like in the exponential equation form?
3 squared equals 9.
Very nice. Yeah, so you are given 2 equals log of 9 with base 3. So that base 3, of course, becomes the base for your exponential function. Remember, your logarithm always equals an exponent. So whatever the answer you have for the log is always going to be your exponent. So yeah, very nice. That becomes 3 squared. And of course, 3 squared will equal 9, which is in the parentheses. And you know, this is with numbers, so of course it's very easy to verify that also. So that's all you got to plug in. Now, as I was telling you, you're not always going to be given, you know, part of your equations. If you look at this example here, they're just giving you the answer box and you have to type the entire thing. So what I want you guys to do is send me your answers through chat. Don't send it just yet. Hold off. I want to give everybody a chance to come up with an answer. So just have your answer ready in the chat. And when I ask you, send it then. So don't send it just now. All right, go ahead, send your answers in. Okay, so they're not actually asking you to solve this because I'm seeing that some of you are actually giving me the answer for C, because what they, as you can see, all they're asking you to write this in the exponential form. So yeah, Noah, what you had was correct. Just we don't want the answer for C, but yeah, you're just converting it back into the exponential notation. So Teddy and Michelle, you guys actually gave me the answer, but you know, I will show you when they want you to actually solve these and come up with the answer for your variable. This one is literally just rewriting your equation from exponential to logarithmic. So Alicia, you've got 1 to the power of C equals 1000. Tessa, you've got 10 to the power of C. I'm guessing instead of plus, you meant an equal to sign? Yeah? Okay. Kalia, very nice. So yeah, What's happening over here, guys? And Alicia, I'm not sure if you put the 1 because you don't see a base on the logarithm. But if you guys will remember, this is coming from our common log. So remember, when there is no base, it's understood that you have a base 10 logarithm because this is your common log. So that's why you are taking 10 to the power of c, which would equal 1000. And you guys are absolutely right. If they asked you to find the value for c, then that would be the number 3. But this is not what they're asking you for here. So you're not solving the equation, you're just converting it. Okay, so that's all you plug in here, 10 to the power of c, and then we come back down equals 1000, and that's it. So you will have a couple different examples where just you're doing these conversions. Same thing's happening over here. This one is actually asking you to convert it into the logarithmic form. So you can say they're giving you part of the answer and they want you to come up with the rest of it. But let's take a look at this guy. So again, we can make sure you guys are comfortable converting this into the logarithmic form. So same thing, have your answers ready in the chat. Don't send the answer till I ask you to, but now you are converting this into the logarithmic form. So let me see what that looks like. So just get your answer ready. Don't send it just yet. All right, go ahead, send your answers in. Oh, Alicia, you're converting this into logarithmic form. Okay, let's see. Noah, Allison, you guys have log of z with base g equals m. Okay, Alicia, okay. Teddy, again, I'm not sure it looks like what you sent me is z times g equals m.
I couldn't figure out how to make it smaller, and I just figured out I could have just put log, but I meant for it to be the log base.
Okay, so which one is your base here, the z or the g?
G.
Okay, that's good. And let me see, Tessa, you've got log of z with base g as m, Dalton log of g. And I know it's kind of hard to put the notation in, just a simple text here, but Dalton, are you saying g is raised to the power of z, or are you saying g is your base? G is the base. Okay, very good. Raylan, that's kind of what yours looks like also. G is the base and log of z equals m. Chloe, log of z with base g equals m. Okay, very good. Yeah, so whatever is the base of your exponential function, of course, ends up becoming the base of your logarithmic function also. And then remember, the exponent is always the answer for your logarithm. So yeah, you are taking log of z with base g equals m. So again, guys, just be sure that you are able to convert these both in both directions. So log with base g, and this will be for z equals m. There you go. Anybody have a question on this? So Alicia, does that help you out? Okay. So again, remember you will have a couple examples where they're going to asking you to convert this. I'm actually going to let you guys work on this for homework, but you know, basically the idea is you can rewrite this as y equals log of x with base 11. They're asking you to find the inverse, you know, which of course means they're asking you to put it in the exponential notation form. So, you know, when you are converting these into the exponential notation, you know, what's going to happen here is since they're asking you to use x as your variable, make sure whatever you type in here is not going to be using the variable y, but it should have the variable x. And I'll show you the next example, so you should be able to use that to help you out with this one. But like I said, I'm going to let you guys work on this as homework, but this is the one we'll work on together. Very similar to the previous example. So we can rewrite this guy. Instead of f of x, we can use y. You have y equals log of x minus 2. So let's convert this into the exponential notation, and let's start out by seeing what that comes out to be. So go ahead and tell me, if you rewrite this in the exponential form, what will our equation look like? Okay, go ahead, send your answers in. Okay, Maciel. Yeah, very nice. Your base is going to be 10. So that will be 10 to the power of y equals x minus 2. Because again, this is the same situation. When you do not see a base, remember it's understood to be a base 10 logarithm because this is a common log. So when we convert this into exponential notation, you will end up with 10 to the power of y equals x minus 2. And then Maciel, what you gave me was the final answer, and that's definitely correct. But yeah, guys, I was just looking for the exponential notation. So Noah, Allison, Dalton, Tessa, that looks good. Yeah, Michelle, that looks good. So once you have it in this form, you know, then of course, to get the final answer, you need to get your x by itself. So all we would obviously do at that point is add the 2, move it to the other side, and you would end up getting x on one side, 10 to the y plus 2 on the other side. So this x is what, you know, because these are inverse functions, so we know x and y have to switch places. So x is where the f inverse notation will come in. And then you have 10 to the y plus 2. But, obviously, since we are using x as the variable in this function, that's kind of what I was mentioning for that example before this. You cannot have y here. You have to replace this with the x. Because remember, your x and y are just names or letters that we are using for the variables. Obviously, you can keep changing those, and that's exactly what we need to do in here. So when you type your final answer in, this will be 10 to the power of x, and then we come back down, and then the plus 2. So this is how you're going to type your answer in. And that's the same thing we will need to do for the example before this. So just make sure whenever you type in your final answer, you do have the same variable as what's given in your function notation. But just another example where you're converting it from the logarithmic to the exponential form. And that's the same thing that's going to happen in this example also. Convert it from one form to the other. Now, this is what I was talking about. When they actually want you to find the value of the variable, they are going to use the instructions of solve. So when they say solve, that means you're finding the solution. And you will see how they're talking about here the solution for x equals. So that tells you, this is what we are looking for. So same thing here. The first thing we are going to do is convert this into our exponential notation, and then you can find the answer for x. So go ahead, solve this, and let me see what answer you come up with. So what do you have? Alrighty, very good. Because when we convert this into exponential notation, you have base 5 raised to the exponent of 3 equals x. And of course, 5 to the third power is 5 times 5 times 5, which comes out to be 125. So yeah, your x value is going to be 125. Very nice. So let's see, that was Teddy, Raylan, Noah, Maciel, Tessa. Very nice. Good job, guys. And they're going to keep changing that location for your x variable where they're going to put it. So if you look at this guy over here, you've got log of 81 with base x equals 4. So obviously, again, start by converting this into the exponential notation. So that's base x raised to the power of 4 equals 81. So, again, you can kind of see how you want to solve this equation and what value do you come up with x. So I'll give you guys a minute to see what you can come up with. Because one way that you can think about this is, how can I rewrite 81 as some number, to the fourth power? because that will kind of help you see what the x should be. And if you have a different thought, then kind of let me know what you're thinking, how you would solve that. So what do you get for your x? Yeah, very nice, because we can rewrite 81. Of course, you can start with 9 times 9, and then we can break each of those 9 down into 3 times 3. So of course, you can see that comes out to be 3 to the 4th power. Now you can think of this as being the reverse of the one-to-one property for exponential functions, because in this case we are saying, okay, our exponents are the same, 4 and 4, so that means our x equals 3. Of course, you can use the idea of taking a 4th root on 81, right, to come up with x equals 3 also. The only thing we have to be careful about is when you take the 4th root of 81, remember, technically you get a positive and a negative answer, but in this case we cannot use -3, because remember, our base, since x is the base, your base has to be a positive number, and remember, of course, the base cannot equal 1. So since we have restriction on what our base can be, of course we cannot use a negative value for our x in this case. So just be careful if you do use the 4th root. Just keep in mind we are only interested in the positive root. We are not interested in the negative root, and that's why you only get one answer, x equals 3 in this case. So you should have a couple more examples with solving for these equations over here. Let's take a look at this guy. So you are given 7 to the power of x plus 6 equals 4. They're asking you to solve for x. As you can see, they want us to get x by itself. And they're also asking us for an exact solution. So that means they don't want any decimal answers. So how do you think you will begin this problem? What do you think you will do as your starting point?
We change it back to logarithmic
Yeah, very nice.
setup. I forgot what it's called.
A logarithmic equation. Yeah, so what do you think this will look like when we convert this into a logarithm?
Would be log of base 7. Okay. 2y with
You're on the right track.
forgetting the other parts now.
Okay, so yeah, you got to think about what are you taking the log on which number or which value, and what are you going to put on the other side?
The value would be a 4, and then it would be x plus 6 on the outside.
Very good. Yeah, a logarithm always equals the exponent. So your exponent always goes on the other side. So very good. Yeah, so you can see we start out with log of 4 with base 7 equals x plus 6. Since they are asking us to solve this for x, that means, of course, you want to get rid of that 6, bring it on to the left-hand side, and then you are basically left with log of 4 with base 7, and then we are subtracting the 6 equals x. Since they asked us specifically for the exact solution, you are not going to find the decimal equivalent for this. This is going to be your answer. So yeah, anytime they say exact solution, they're basically asking you to leave the logarithm as it is. So this will be log with base 7 for number 4 minus 6 at the end. Anybody have questions on this? Okay, same thing here. They're asking you to solve for x and find the exact solution. So, work through those kind of examples. And as always, if you're not sure about anything, you get stuck, I'll definitely help you out with that. So this last part here that I wanted to look at is, just the application with logarithms. So, these were the examples that we were, using conversion from one form to the other. So you've got examples of that in your handout. I just wanted to point out, you also have the one-to-one property for logarithmic equations like we did for exponentials. So the idea is the same thing. As long as your base A is going to be the same, we can basically say x1 is equal to x2. So very similar to the one-to-one property with exponential functions. So as long as your bases on the logarithm are same, we can say these x values will be equal to one another. And sometimes we use that to solve logarithmic equations, but for the most part, by converting them into the exponential notation or taking exponential functions and converting them to logarithmic equations is easier to solve. So you've got several examples of that in your handout over here. And then this last example is the one we're looking at in my MATLAB. So if when you're working through your homework, you need extra help, you can definitely look at this example in your video lecture and that would help you out. But we'll go ahead and solve this one together. So this one is telling you how long does it take for a deposit of $1,100 to double at 1% compounded continuously. So since they're talking about compounded continuously, remember this is the PERT formula. So A equals P times E to the power of RT. They're talking about a deposit of $1,100. So of course that's a deposit, which means that's our principal, the P value. They're telling us that we are doing this at 1% interest rate. So that's of course the R value. They're asking us how long does it take. So if they're talking about how long, that's your time. So that's of course T, and T is going to be an unknown value over here. So if T is our unknown value, we are given R and P. Of course, E is the natural number E, so that means they should actually also give us the A value. And the A value is coming from here when they're telling you the deposit is going to double. So that's of course going to be our future value, the A value. So we've got A, P, R, and T. T is of course the value we are trying to find. Our rate of interest is 1%, so as a decimal, that will be 0.01. The principal is a deposit of $1,100. So what do you think the dollar amount for A is going to be in this case? What are you going to put for the A value here?
Would it be 2,200?
It will be very nice because they're telling you your dollar amount is doubling. So basically just take 1,100 times 2, and that's going to give you your A value of 2,200. So in our formula, A is 2,200, P is 1,100. We're multiplying it by the natural number E. And then as our exponent, we will have R, which is 0.01, and then multiply that by T. So as you can see, since our T value is the unknown and that unknown value is in the exponent, that's actually when we know we have to use logarithms, because anytime the unknown variable is going to be in your exponent, we will have to use logarithms to bring it down to the base level so that we can solve it. And so let's clean up this equation a little bit. Since you've got 1,100 being multiplied into the natural number E, we're going to go ahead and divide it on both sides of our equation. And then of course, on the right-hand side, we are just left with e to the power of 0.01 multiplied by t. What do you think we'll end up getting on the left-hand side here?
$1,100.
No, you're dividing, right? You're not subtracting.
Oh.
Yeah, very nice, Kalia Dalton. Because you're dividing, so 1,100 goes into 2,200 two times. So it's actually kind of neat because when they tell you that your dollar amount is going to double, that's again a good way to see that, yeah, you will get 2 on the left-hand side. Now, once you clean up your equation and get to this stage, this is basically your equation in the exponential notation. So we will now need to convert this into our logarithmic equation. So since that's a base e, remember you will use natural log because that's log with base e. You just don't write it out as a logarithm with base e. So convert that base e into a natural log, and that will of course be at number 2. Because remember, a logarithm always equals the exponent. So you will end up by converting this, natural log of 2 equals 0.01 t. And then, you know, of course, all you have to do is get your t by itself. So since we're multiplying, we will take that 0.01 divided on both sides. And can you tell me what kind of answer you are coming up with for the t here? Oh, and one thing I do want to point out, when you are doing this in your calculator, when you use that natural log key, a lot of times, you know, calculators automatically open parentheses. So when you type that in the 2, make sure you close parentheses before you divide it by 0.01, because if you don't close the parentheses here, your answer will come out to be inaccurate. So what do you come up with for the value of t here?
Are we supposed to get a decimal?
You will,
Okay, never mind.
So what did you end up getting?
69.31.
Yeah, okay, looks like that's what Alicia, Michelle, Raylan, Dalton, you guys are coming up with. Okay, so as a raw answer, you actually have 69.31471,806. And we're actually going to need all of those decimals, so you definitely don't want to get rid of them. So what this means, remember your time is always by default in years. So we're saying right now it's going to take 69.31471,806 years. So the 69, the whole number part is definitely in years, but then you know what we will have to do, because as you can see, they're asking us for the time here in years and days, right? So we actually need to take that decimal part and convert it into days. So once you have those 69 years, we'll go ahead and put the 69 in here. But then for the days, we'll need to do some calculation. So the first thing you're actually going to do is from the 69, go ahead and subtract the 69 because we don't need that whole number part anymore. So we'll go ahead and subtract 69 from this. So that will leave us behind with just the decimal answer, 0.31471,806. And once you are left with the decimal part, then just multiply that by 365 because that's how many days we have in a year, and you will be able to convert this into years. So go ahead and tell me what you come up with when you take the decimal part and multiply by 365. So make sure you subtract that 69 first, so you only have the decimals. So how many days other than 69 years will it take?
It's 114.8720904.
Alrighty, very good. So 114.8720904. So yeah, use your rounding rules because you have that 8 after your decimal. So this will actually round up to 115 days. If this number after the decimal point was 4 or less, then you wouldn't round up. So straightforward rounding rules, 5 and up, you go 1 unit up, 4 or less, it stays the same. So that means we are looking at a total of 69 years and 115 days. And it makes sense because you're only getting a 1% interest rate. So your money is not growing as fast. If you had a 6, 7, 8% interest rate, then you wouldn't need 69 years for this money to double. But because your interest rate was so small, it makes sense that it's taking us a longer time to get this amount to double. Did anybody have question on any of this? Okay. And like I said, you do have a similar example for this one in your handout. So if you do get stuck, obviously go ahead and take a look at that. And I believe this is actually the last example in your homework. So just an application for that. So that was just your basic, introduction into logarithms with the graph and how you can solve some of these logarithmic equations. But as you can see in section 4.3, we are getting into rules of logarithms. So I had asked you guys to review the rules for exponents. So if you've actually done that, then you will see how these rules tie up from exponents into logarithms. So we are starting out with our product rule over here. So with product rule, for the exponential functions, of course, when we are multiplying two numbers that have the same base, then your rules of exponents basically say you can go ahead and add those exponents together. So we keep the base 2, add 3 plus 2 in your exponents, which ends up giving you 2 to the power of 5. So you can kind of see how this will translate into our rules for logarithms. 2 to the third power can be written as log of 8 with base 2. 2 to the second power will be log of 4 with base 2. And then, of course, 2 to the fifth power is log of 32 with base 2. So you can see the way this rule translates for logarithms. If I take log of 8 and I add that with log of 4, 8 times 4 gives me 32. So that's how you come up with the answer. So remember, with multiplication goes addition. So you can use this rule to try and rewrite 2 logs into a single log. So I can take log of m, add that with log of n, as long as both of them have the same base a. And that combines into log of m times n with base a. So you've got a couple examples over here to highlight how these product rules would work with logarithmic equations over here. So let's take a look at how you can use these rules in your examples here. So, just something as simple as this guy here, you have natural log of 3 and natural log of 4. So of course you can see, since both of them are natural log, we know they're both base e. So we do have the same base, in our function. So all you have to do with that product rule, since they're asking us to combine this into a single logarithm, all you have to do is take your values inside the parentheses and multiply them together, you know, keeping that natural log. So 3 times 4 will of course end up giving you natural log of 12. And that's all you do with a product rule. Send this guy here. Come on, buddy. There we go. Natural log of 12, and you're good to go. You know, it can be in a form like this also. So again, using that same idea of the product rule, let me see which answer do you think would satisfy this example here. Option A, B, C, or D.
Would it be D?
Would it be D? Okay. Dalton, you're also saying D. Jacob, D, okay. So what's making us choose D as the example? What are you guys kind of thinking with the answer D?
Because when you multiply that x plus 8 and the x plus 5 together, you have to do the FOIL method with it. So you'd get the x squared plus 13x plus 40.
Yeah, very nice. Very good. And you know, again, just always make sure your bases are the same before you use the product rule. And that's exactly right. You are using FOIL because obviously we end up multiplying what's inside the parentheses. And since these guys happen to be binomial terms, yeah, you definitely need to take a FOIL on these. So you end up with the answer from part D, as you said. So that gives you x squared. Of course, that would be 5x. 8x from here. And then, of course, 5 times 8 would end up giving us 40. And then when you combine these terms in the middle, you would have your 13x. And that would be the result of your FOIL. So yeah, very nice. And then, you know, as you can see, once you go through this process, obviously none of the other answers even make sense because first of all, we're not dividing anything. So you should not have B or C as your answers. And of course, you can see the only way you would get answer A is by adding these numbers, not multiplying them. So remember, for the product rule, if you're adding 2 separate logarithms, you actually have to multiply the values to get a single logarithm in this case. Alrighty, very good. We can check that. Okay, so this is now getting into our quotient rule. So again, the quotient rule for exponential functions is if you have the same base and you are dividing them, then in this case, you take that base 2 and then we subtract our exponent. So the top one, the top exponent goes first minus the bottom exponent. So 5 minus 2 will give us 3, and that's how we come up with 2 to the power of 3. So you can see with division goes subtraction. And so here the idea is you take the value on the numerator and that becomes part of the first logarithm. You take the value of your denominator and that becomes the second logarithm. So make sure this order is really important when you're working with the quotient rule. So when you have log of m divided by n with base a, log of m goes first minus log of n, and of course we keep the common base in this case. So again, you've got a couple different examples for this in your handout, but let's go ahead and look at this guy here. So we are given log of 140 with base b minus log of 10 with base b. So when we combine this using our quotient rule, of course, we would keep that log with base b, and then you are using division. So that's going to be 140 on the top divided by 10 on the bottom. So what do you think your final answer will come out to be in this case? Yeah, anytime you are working with fractions, you have to reduce your fractions. Even if they don't tell you that specifically, make sure you're always reducing your fractions. So inside those parentheses, you will need to divide that 10 into the 140. So that would, of course, end up giving you just log of 14 with base b. Alrighty, very nice. So this guy will be log base b, and then for number 14. Alrighty. Okay, what do you think for this one? A, B, C, or D? Which one would you go for using the quotient rule? And we know we're using the quotient rule because you're subtracting those two logarithms. So A, B, C, or D? Okay, Maka, you're going with A. Dalton, you said C. Noah, Allison, you guys are going with C. Okay. Jacob, you're also saying C. Raymond. Okay, so it looks like Maka is the only one who's choosing A. And let's see, Chloe, you also said C. Okay, let's take a look at this guy. So here, of course, again, we are using the quotient rule. So since both of them have base A, we can combine these. So let's see, your x squared minus 4 will go on the top, and the x minus 2 will go on the bottom. And again, like I said, since these are fractions, we do have to reduce our fractions. Now, x squared minus 4 is, your difference of squares. So x squared minus 4, we can actually rewrite it as x squared minus 2 squared. And then you can use factoring on this, and this guy factors into x plus 2 and x minus 2. So what happens is when you simplify your, fraction in a way over here, I can rewrite my numerator as x plus 2, x minus 2. Our denominator is x minus 2. So as you can see, those two common factors will end up canceling each other out, leaving you with log of x plus 2 with base A. And so, yeah, as you can see, it definitely comes out to be option C in that case. So Maka, does that help you out? And then, of course, when you compare it to options B and D, you will obviously see those guys were not even close to what our answer should have been. So very nice. It should be option C in this case. So just different, examples using your product rule and quotient rule. So another example over here, let's take a look at this guy. So again, tell me which option would you go with to rewrite this expression as a sum or a difference of multiples of logarithms. So A, B, C, or D.
Would it be C? Or not C, D?
B as in boy or D as in dog?
Oh, wait.
Boy. Okay, so you're saying either B as the
Uh.
answer. Okay, let's see. Michelle, you're going with D. Raylan, you're going with B. Jacob, Dalton, okay. Tessa, okay. Noah, Allison, okay. So what's happening over here, you know, of course, as you can see, we are again given x squared minus 16 inside the parentheses. So you can again use the idea of difference of squares, because I can rewrite that 16 as 4 squared. So this guy will factor into x plus 4, x minus 4. So you can basically have log of x plus 4, x minus 4 if we just go ahead and factor that out. So you can see, since we are multiplying the x plus 4 and x minus 4, this is where we would use our product rule. And that, of course, would then come out to be a plus. Remember, because addition goes with multiplication in these rules. So this would split up into log of x plus 4, and then you would add log of x minus 4. Now remember, since this is the product rule, you can always have x minus 4 here and x plus 4 over here, you know, if I had switched the order of these two factors. So for the product rule, you know, these numbers can definitely interchange, because I think that's what we have over here. Yeah, they have x minus 4 as the first one and x plus 4 as the second one. So these pairs can definitely change. And so, yeah, very nice. Our answer is going to be option D. So Teddy, does that make sense? You know, really, when you have just x squared minus 16, we cannot just split up the x squared as one logarithm and 16 as the other one. So, you know, just be careful when you're working through these examples here. Okay, so I guess we should go ahead and check that. You will have quite a few different examples here, you know, using these rules. Now, the next one we're actually looking at is the power rule. So again, for exponential functions, the idea is if you have the base 2 with two different exponents, 3 and 2, the rule is, you know, you keep that base and then you end up multiplying these exponents. So 3 times 2, of course, ends up giving you 6, and we end up with 2 to the 6th power. So basically the idea is you're multiplying the two exponents together. So the way it works out with the logarithms, we know log of 8 with base 2 is going to equal an exponent also. So you're taking this exponent 2 and multiplying it with your logarithm. So basically the idea here is, with these power rules for logarithms, you take your exponent 2 and bring it in front of its own logarithm, and you end up multiplying them together. So as you can see with the rule over here, we're taking this exponent n and we're bringing it in front of our logarithm and multiplying. And you know, of course, you can reverse that if you had to go in the opposite direction, if we were combining all of our logs into a single log. So you've got, again, a couple of examples over here, but let's just look at something like this. So we can see we have log of 2 squared with base a. So I can take that exponent and I can bring it in front of the logarithm itself. So you will end up getting 2 times log of 2 with base a, and that's it. Just using your power rule, we can simplify this. So 2 times log of base a with 2. There we go. Now, of course, you will see multiple different versions of this rule also being used. So what do you think about this guy? How are you going to rewrite this using the power rule? Step 1 is going to be taking the 6th root of 3 and rewriting it as some base with some exponent before you can use the power rule. So how can you rewrite this 6th root of 3? Actually talked about this. I think it was chapter 1. So I know it's been a while, but we had talked about how to rewrite these radicals in the exponential form. Very nice, Alicia. Yeah, you are going to rewrite this. So basically the rule is, if you have a base with a fraction in the exponent, we call them as rational exponents. So that number on the denominator actually becomes the index of our radical, and that m is your true exponent. So you can still write that as an exponent of a to the m, or technically you can have a square root, nth root of a, and you can also put that exponent on the outside. So when we're looking at this as the 6th root of 3, that means in the exponential notation, the 6 is going to become your denominator. And obviously, whenever there is no exponent, we know you can write 1 as your exponent. So this guy will become 3 to the power of 1/6. Now, Michelle, you actually had the answer of 3 to the 6th. So if you think about this, 3 to the 6th power, of course, ends up giving us a fairly large number, because 3 to the 6th power will end up giving us 729. But if you think about 3 to the 1/6, or basically think about the 6th root of 3, you are actually going to end up getting a pretty small answer in this case, because you will end up getting 1.200936, and it's going to keep going. So 3 to the 6th is of course not going to be the same as 3 to the 1/6. So keep this rule in mind. When you have a radical notation, when you convert it to the exponential form, you should have a fraction where the index of your radical is going to end up becoming the denominator on that exponent. So once you can rewrite this logarithm as a natural log of 3 to the power of 1/6, then of course we can use our power rule, and we can take that exponent, bring it to the front. So we will end up getting 1/6 times the natural log of 3. So that's kind of how the progression of this problem is going to work out. So we will have 1/6 and then natural log of 3. Oops. Questions on this one, guys? Again, you will have a bunch of different examples with this. Some of these are a little bit more specific because you can see for this example, they are saying specifically to rewrite log of 35 with base A in terms of log of 7 and log of 5. So how do you think you can rewrite that 35 in terms of 7 and 5? Okay, let's see. Noah, you're going with option B over here. So log of 7 plus log of 5. Okay, so let's take a look at this guy. Dalton, you're doing the same thing, Jacob. So when you are given log of 35 with base A, you know, of course, we can rewrite 35 as 7 times 5, right? So that means you're going to be using the product rule over here. And then by product rule, you would have log of 7 plus log of 5, and you know, of course, keeping that same base A on your logarithm. So yeah, very nice. This takes us to option D. So as I'm showing you with these examples, you know, all of these are just different forms of using these product, quotient, and power rules. Now, you know, sometimes you may have to use, oh, I guess I didn't check my answer. You know, sometimes you may have to use multiple different rules. Now, I'm actually just going to walk you through this, but I want you to try this on your own when you do your homework. So, of course, you know, since you can see you have a square root on your 1280, you know, obviously convert it to your exponential notation, then you can use the power rule. But you will see they're specifically asking us to rewrite this in terms of log of 2 and log of 5 with base A. So my recommendation would be to try and see what you can break down, you know, this 1280 into, because you're looking for something which would be, you know, multiples of 2s and 5. So you want to see if you can come up with something like that, and then use, you know, that breakdown to help you come up with logs of 2 and 5. So I want you to try this. You get stuck, you know, I'll definitely help you out, but I want you guys to try working through this example on your own. Right, let's take a look at this guy here. So this one is asking us to rewrite the expression as a sum or a difference of multiples of logarithms. So can you tell me which rule you would use to break this down? So product, quotient, power rule, which one would you go with? Yeah, very nice. Product rule, because, you know, of course, you are given log of 13x, so that's 13 times x. And since you're multiplying those two numbers, you can break this up into log of 13, of course, with base 4, and log of x with base 4. There you go. So now, you know, of course, they're having us split this up into multiple logarithms. Now, this one here is, again, very similar to what you just did with that 13x, except your x is in a square root. So you still want to start out with the product rule, because obviously we are still multiplying 22 with the square root of x. So once you start out with your product rule, what will you need to do next to simplify this further?
I would use the power rule on the x, square root of x.
Yeah, very nice. Exactly what you saw with that, what was it, 6th root of 3. So you would have log of 22, which would stay as it is. We can rewrite our log of square root of x as x to the exponent of 1/2. And then, yeah, like Noah said, use your power rule to simplify it. So bring that 1/2 in front, remember, of its own logarithm. So log of 22 plus, and then you would have 1/2 times log of x. Okay, so simplify it all the way through, and this is what you should end up with. So as I was kind of saying, sometimes you can have a combination of different rules. You don't always have to have only one rule that you are using. So this is kind of what this guy will come out to be. Questions on this one? So you will have, a couple different examples where they are going to ask you to use, combination of rules. This one again is asking you to rewrite it as a single logarithm. And actually, I do want to point out one thing. You see how you have that 9 times log of x with base 7? So you will be reversing your power rule in this case. So for this example, you would have to take, you will have to take this 9, and since the 9 is being multiplied into the log, that's how we know this is the reversal of your power rule. So when you put it back, you should have log of 2 with base 7 plus log of x to the 9th power with base 7, because this is us reversing the power rule. And then now they're asking us to combine this into a single log. So since this is an addition symbol over here, of course we know that comes from the product rule. So when you combine this into a single log, you will multiply 2 times x to the 9. So this is kind of how you have to go backwards when they're asking you to combine it into a single logarithm. So of course then this will become your final answer. Practice with these. It may take a little bit of practice, to work with these. Same thing's happening here. They're asking you to rewrite this into a single logarithm. So you will need to use, these different techniques. So I want some of these examples that you should try on your own. And then, of course, you have all different types of examples in your video lecture. If you have not looked at the video lecture, I would highly recommend you to go back and take a look at it. So after these 3 rules, the next one that we are looking at are the inverse rules. If you actually, again, look at the inverse section in section 2.5 in chapter 2, we had talked about, what happens if you do composition with inverse functions. So they're actually bringing those same rules over here, and they're calling it inverse rules. So the idea is when you do the composition between 2 inverse functions, which in this case are exponential and logarithmic, your answer always comes out to be that variable x you started out with. So it looks like this with our inverse rules for the exponential and logarithmic. So look at that rule number 1. We have log of a to the x with base a. So of course you can see how both our base a's here are the same. So essentially what we're saying is that your log of base a and base a from your exponential function cancel out, leaving you with this x as your answer. For rule number 2, we have the exponential base a raised to the power of log of x with base a. But again, you will notice our base a and base a here are the same. So again, the exponential a is canceling out the log base a. And again, this x ends up becoming your answer. So again, you've got a few different examples here in your handout, but in your homework, those were, I think, the first couple examples we had skipped over. If it will let me click on this. Okay. So right over here, these are actually your examples from your inverse rules. So you can see how, again, our bases for both the exponential part and the logarithmic base are going to be the same. So here, since we have base 3 here and base 3 here, like I said, essentially, you can kind of think of them canceling each other out, and you just end up with whatever, our x value, or in this case, whatever inside our parentheses is going to be. So you just end up with 4x plus 6 as your answer over here. So this is coming from your inverse rules. So pretty straightforward, as long as you keep in mind that if your bases are going to be the same, then x is going to be your answer. This next example over here is also based on inverse rules. So here you can see how we are given natural log of e to the power of 4x. So we know natural log is also obviously a base e logarithm. So again, you can think about how this natural log is canceling out this base e. So you end up getting, just that exponent 4x as your answer. So when you are choosing the option over here, you're looking at that 4x as the answer. So remember, these, like I said, are coming from your inverse rule examples. So this one over here is actually summarizing all of these rules that we have looked at. It looks like you have a lot more rules than we talked about, but they're actually modified versions of each other. Now, these rules over here with base A and these rules over here with natural logarithms are actually the exact same rules. They're just talking about base A over here, and of course, they're just talking about, natural log over here. But if you compare all 8 of these rules, they are the same. So these 2 rules over here, 1 and 3, are actually based on your inverse rules. Rule number 4 over here is also based on the inverse rules that we just looked at. You should recognize rule number 5 as your product rule. Rule number 7 is your power rule. Rule number 6 is your quotient rule. And honestly, rule number 8 is also based off of the quotient rule. So they're just, like I said, splitting it up into, 8 different rules. But all of these are the rules that we have already talked about. And this rule number 2 is actually coming from the exponential rule that when you have a to the 0 exponent, you get 1 as the answer. So when we convert that back into logarithmic format, you end up getting rule number 2. And of course, those are the same rules you can compare here with the natural log. For that matter, you can do the same rules with common log. So this is a nice little summary where you get to see how these rules can be broken down. And, again, you've got a bunch of different examples to kind of help you walk through that. I really like this table over here because this is showing you the comparison between the exponential rules and logarithmic rules. So you can always come down here and use this as a reference when you're going through your examples or quizzes and exams. So just kind of keep in mind that you have all of these different resources in your handouts. And then next class, we'll pick up from our base change formula because I do want to take some time and talk about those. So, look through these examples. Anything that you get stuck on, you need help with, please let me know. And then we'll definitely finish 4.3 and 4.4 in class on Thursday. And then remember, Tuesday is going to be your exam day for chapter 4. So please let me know if you guys have any questions. And if not, then I will see you on Thursday morning. Take care, everyone. Be careful. Stay safe. Bye, guys.
Bye.
Bye.